Hey everyone, welcome back. Ready for another deep dive.
Always.
Today, we're going deep into the world of Wolfgang Pauli,
Ah,
a
Pauli.
physicist. Maybe not a household name, but
But his work touches every single one of us every day.
we've got a lot to cover: biography, academic papers that'll make your head spin.
Even some philosophy thrown in for good measure.
Pauli was brilliant, that's for sure.
A Nobel Prize winner. But he could be a little prickly, challenging everyone.
Even Einstein. Our goal today, not just to list his achievements, but
But to understand them,
Huh.
how did this guy, working with the tiniest particles imaginable?
end up shaping the world we experience.
Exactly.
All right, so let's start at the beginning. Pauli's born in Vienna, 1900.
Into a family that was, well, intellectually charged, you could say.
His dad, a chemist, mom,
Yeah.
came from a family steeped in the arts. So Pauli's got this.
This incredible blend of influences from a young age. Schneeppot, the author we're drawing on today.
Yorgo Schneffe, yeah.
He really emphasizes how this early environment shaped Pauli, this interest in science, but also the big philosophical questions behind the science.
And this kid's a prodigy, right?
Oh, absolutely. Publishes a groundbreaking analysis of Einstein's theory of relativity.
Hold on. How old is he at this point?
20.
20 years old. I was barely figuring out laundry at 20. But, okay, so, genius. But what's Pauli really known for?
The exclusion principle.
The what?
Imagine this. You're trying to fit electrons, those tiny particles whizzing around atoms.
Okay, I'm picturing it.
You're trying to fit them into specific energy levels like seats in a theater.
Gotcha.
Pauli's exclusion principle says 2 electrons in an atom can't be in the exact same state. Like, each seat needs a unique ticket, row, seat number, and a specific orientation of the electron's spin.
So it's like a cosmic seating chart for electrons. But why should I, the average person listening, care about where these tiny electrons sit?
Because without this principle, the world, as we know it, wouldn't exist. It dictates how atoms are structured, how they bond to form molecules.
Which make up everything.
Exactly. You, me, this microphone. All thanks to the exclusion principle.
Okay, I'm starting to see how this seemingly tiny thing
Yeah.
has huge implications. Give me an example, something concrete.
The periodic table, you know that chart from chemistry class?
Oh yeah, vaguely.
It's organized by the number of electrons elements have, and those electrons are arranged in specific energy levels because of Pauli's exclusion principle.
So without it,
all the elements would basically act the same. No diversity of chemical reactions.
no delicious food, no colorful clothes,
No complex medicines.
all because of how electrons are arranged. Wild. And Snippet, he really makes this point, right?
Absolutely. He says the exclusion principle isn't just theoretical, it's the very foundation of chemistry, which then leads to biology. It's the bedrock.
You mentioned something earlier about white dwarf stars.
Ah, yes, these are stars so dense gravity's trying to crush them into oblivion.
Sounds intense.
What stops them from totally collapsing? You guessed it, the exclusion principle. The electrons inside are packed so tight.
They need their space.
They do. They're forced into their highest possible energy states, and the principle prevents them from all collapsing into the lowest state. Creates an outward pressure, fights back against gravity.
So this tiny principle is literally holding up stars. My mind is officially blown. But Pauli didn't stop there, did he?
Oh no, not even close. He's also a key figure in the development of quantum mechanics.
Quantum mechanics, that's like a whole other level of physics, right?
Exactly. Think of it this way. Classical physics, Newton's laws, they work great for everyday stuff. Apples falling, planets orbiting.
Makes sense.
But zoom in to the level of atoms and particles. The rules change. That's where quantum mechanics comes in.
And Pauli was right there in the thick of it.
Oh yeah. Working with Niels Bohr, Werner Heisenberg, the big names. Schneeppot even talks about how crucial Pauli's insights were to shaping their understanding of the quantum world.
So he wasn't just like along for the ride. He was actively contributing.
Absolutely. One of his key contributions, Pauli matrices. It's a set of mathematical tools.
It's complicated.
A bit, yeah. But they essentially give us a way to represent the spin of an electron.
So it's not just where the electrons are, it's also how they're spinning.
Exactly. And understanding that spin is crucial. Explaining how atoms behave in magnetic fields. Even developing new technologies, like quantum computers.
So we're already seeing the ripple effects of Pauli's work, even back then.
Oh, absolutely. And, Schneeppot points out something really interesting. He says, Pauli wasn't afraid to challenge anyone, even the most respected figures in physics. He was constantly pushing for clarity, for deeper understanding.
So he was brilliant, he was bold, and he wasn't afraid to ruffle some feathers. This is shaping up to be quite the deep dive.
Oh, it is. And we're just getting started. Pauli, he wasn't just, tweaking the theories that were already out there. He was bold. In 1930, he goes ahead and proposes a whole new particle.
Hold on. He just invented a particle out of thin air.
Well, not exactly thin air. There was this problem bugging physicists, beta decay. You familiar?
Refresh my memory.
So you've got a neutron in an atom's nucleus, and it decays, becomes a proton and an electron.
Right, okay.
But the energy, it didn't add up. Like some energy was just vanishing.
A cosmic accounting error.
Pretty much. And it violated a fundamental law of physics. Conservation of energy. Energy can't just disappear.
So Pauli's solution is invent a new particle to make the math work.
Exactly. He says there has to be another particle, one we haven't detected yet, carrying away that missing energy. He called it a neutron at first.
Confusing.
Yeah, later renamed to neutrino to avoid, mixing it up with the actual neutron.
Makes sense. So what's so special about this neutrino?
Pauli thought it had no electric charge, almost no mass. And here's the kicker. It would interact so weakly with matter.
Meaning?
Practically impossible to detect, at least at the technology they had back then.
So he's proposing a particle that's basically invisible, a ghost particle. I bet people thought he was nuts.
Oh, plenty did. Schneppat even quotes Pauli joking about it, saying, "I've done a terrible thing. I've postulated a particle that can't be detected."
He had a sense of humor about it, at least. But he was serious, right? Like he really believed it.
Absolutely. He understood the laws of physics. Energy can't just vanish. Something had to be carrying it away, even if we couldn't see it.
So, drum roll, please. Was he right? Did they ever find this neutrino?
They did. 26 years later, in 1956, they get experimental evidence for the neutrino. Boom. Pauli's vindicated. Genius confirmed.
Talk about a long wait. But why are these neutrinos so important? What do they actually do?
Well, now we know they're fundamental particles, like a basic building block of matter, and they're everywhere. Zipping through us right now.
Jane, to feel them. But they matter, right? Like for understanding the universe.
Big time. Processes inside stars, how the universe evolves. Neutrinos are part of it all.
Okay, so we've got this exclusion principle governing how matter behaves, his role in quantum mechanics, and now this neutrino prediction. Is there anything this guy didn't do?
Well, Pauli's curiosity, it went beyond just physics. He was also fascinated by the philosophy of science. Like, what do these discoveries mean? Schneppat really highlights this in his essay.
That's what I love about these deep dives. It's not just facts and formulas. It's about the big ideas.
Exactly. And this quest for deeper meaning, it led Pauli down a rather unexpected path.
Oh, where to?
He starts this long-running dialogue with Carl Jung.
Wait, the Carl Jung, the psychologist. What does quantum physics have to do with psychology?
More than you might think. Both of them, they were pushing the boundaries of their fields, challenging the accepted norms.
And they found common ground.
In a concept called synchronicity.
Synchronicity. I've heard of it, but not sure I fully get it.
So Jung, he described it as meaningful coincidences, events that can't be explained by cause and effect, but feel connected somehow. Like when you think of someone and then they call you out of the blue.
Okay, yeah, I've had that happen. Spook me out. But how does this relate to Pauli and his physics?
Well, quantum mechanics, it had already kind of messed with that classic idea of a clockwork universe, strict cause and effect. But now you've got particles behaving like waves, uncertainty built into reality, the observer influencing experiments.
So Pauli's thinking maybe there's more to the universe than we can see. More than just physical laws.
Yeah, he was intrigued by the connection between mind and matter. Like maybe there's this realm beyond our current scientific understanding.
Where things like synchronicity operate.
Exactly. He saw parallels between how things happened in the quantum realm, seemingly without cause.
And Jung's idea of synchronicity.
Right. Like maybe consciousness itself plays a role in shaping reality. We just don't know how yet.
Okay, now we're getting deep. This is getting pretty philosophical. But it sounds like Pauli, he was open to those big questions, even if they took him outside the comfort zone of traditional science.
Oh, absolutely. That's what makes him so fascinating. This fearless pursuit of truth, wherever it led.
So we've got this exclusion principle, the neutrinos, Jungian psychology. How does it all fit together? What's Pauli's lasting impact?
That's a great question. And that's what Schneppat tackles in the last part of his essay. To really understand Pauli's legacy, we need to look beyond the individual discoveries and see how he influenced the entire scientific community.
All right, we're back. We've been deep in the world of Wolfgang Pauli, and let me tell you, this guy's mind. amazing. The exclusion principle, neutrinos, even dipping his toes into psychology with Carl Jung.
Right. Schneeppert, in the final part of his essay, he makes this point that Pauli's legacy, it goes way beyond just his discoveries. It's everywhere.
Okay, so I'm ready for the so what moment. How does all this, like, super complicated physics actually affect me today?
Let's start with something you probably use every day, your smartphone.
Always on it.
Those tiny transistors, they power everything, right?
Yeah.
Our digital devices, the internet, the whole information age. Well, those transistors, they rely on quantum mechanics, specifically how electrons behave in semiconductors. And guess what dictates that behavior?
Is it going to be the exclusion principle again? Because I'm starting to see that Pauli's fingerprints are everywhere.
You got it. It's the reason we can manipulate those electrons, create the logic gates that make computers work.
So no Pauli, no smartphones, no doom scrolling on social media.
Pretty much. Our digital world wouldn't be the same. And remember, superconductors.
You mentioned them, yeah.
Ugh.
Something about zero resistance.
Exactly. Imagine power grids that are super efficient, no energy loss, levitating trains, computers that are lightning fast.
Okay, now you're just showing off all the cool future tech. But how does Pauli tie into this?
The theory behind superconductivity, how we actually engineer these materials, it all comes down to understanding how electrons behave at the quantum level, which, as we've seen, Pauli basically wrote the rule book for.
So a world powered by super efficient energy, all thanks to Pauli.
It's a real possibility. And then there's quantum computing, one of the most exciting fields out there.
Quantum computing. I hear that term thrown around a lot, but
It's basically harnessing the weirdness of quantum mechanics to do calculations that normal computers can't even touch.
give me an example. What kind of calculations?
Designing new drugs with incredible precision, modeling complex climate systems to understand climate change, maybe even breaking the encryption that protects our online data.
Okay, yeah, that's pretty big. But how does Pauli's work from, like, almost a century ago connect to that?
Remember those Pauli matrices? The math that describes how electrons spin?
Vaguely.
They're essential for understanding how qubits work, the building blocks of quantum computers.
So Pauli's math is helping us build computers that could change the world.
Exactly. And while it's still early days, the potential is huge.
This whole deep dive, it's really shown me how these fundamental discoveries in science, they have these ripple effects. They shape our world in ways we don't even realize.
That's it. And Schneeppert, he ends his essay by saying, science isn't just facts in a textbook. It's a process. It's about discovery, debate, and, even a little bit of philosophy thrown in.
And Pauli, he was all about that. Wasn't brilliant, bold, always pushing the boundaries.
He truly was. And who knows, maybe his work, even the stuff with Jung and synchronicity, maybe that'll inspire future scientists to keep asking those big questions, even if they lead to unexpected places.
This has been an amazing journey. I feel like I've got a whole new appreciation for physics, for Pauli, even for the universe itself.
It's been a pleasure diving deep with you. And to everyone listening, if you want to learn more about Wolfgang Pauli and his incredible legacy, be sure to check out the show notes for links and resources. Keep exploring, keep questioning, and we'll catch you on the next deep dive.